This lecture is the fourth one in our derivation of the radiation from a magnetic dipole moment. Um, and so it actually is pretty much just going to summarize it. So what we found is that the power from a magnetic dipole goes as omega to the fourth, just like the power of electric dipole. So I took the ratio of the two, and a lot of the terms cancel out. And what you're left with is just the ratio of the magnetic dipole moment squared over the electric dipole moment squared divided by the speed of light squared. So the last thing I wanted to go over was to take this expression and now put into it that the magnetic dipole moment is the area of the loop times the current. The magnitude of the dipole moment is the charge times the distance between the two charges. The current we can think of as the charge times the frequency, how the angular speed of the charge going around the loop. And just for convenience, we're going to set the distance d being equal to the circumference of our circle. And so when we put all that together, what we get is that a frequency times the radius of our current loop. So now if we put that into our expression for the ratio of the powers for the two cases, what we get is omega b over c quantity squared. Now, if you remember from approximation 2 in a previous lecture, approximation 2 it said that omega b over c was small. So essentially what we're doing is we are considering the size of the current loop to be essentially bigger than the wavelength of the radiation, or the what this works out to be is that the essentially this quantity is small. So we're picking a loop which is much smaller than the size of the wavelength. Okay, so in that case, if we put that in, that means that the ratio of the powers of magnetic dipole to electric dipole is small squared. So that means that this is a small quantity. Or, put another way, the power from a magnetic dipole is much smaller than that of an electric dipole, given that all the conditions are the same. If we're using the same amount of charge in the current loop as the charge that we're oscillating in the electric dipole, then what you should find is that the radiation from a magnetic dipole is much smaller than the radiation from electric dipole. So electric dipoles are going to produce greater amounts of radiation than their magnetic counterpart. So in the end, what you have is these two cases, one with the oscillating current So this is the magnetic case. And then the electric case, we said, was this positive and negative charges. And in this case, the magnetic charges were oscillating back and forth. And in this case, the current was oscillating back and forth. And what you should get is radiation from both. But what we find is that the electric case produces more power than the magnetic case, which is something to consider now if we want to actually do something useful with these, as opposed to just studying them theoretically. That if you want to do something like produce a transmitter, then you're probably going to boost your power by using an electric dipole, oscillating, having a alternating current essentially, or oscillating the charge back and forth, as opposed to this circular the circular current going around in a wire. Okay, so in the next lecture, what we're going to do is we are going to study an arbitrary charge source. So these two are kind of like very simplified cases where you have electric dipole and magnetic dipole. Now what we want to do is to use an arbitrary charge distribution and see what kind of radiation will be produced if we have the oscillating charge inside of just an arbitrarily shaped charge distribution.